Hello, everyone. Welcome to the talk. So today our topic is about how to build a stress streaming connector for continuous application. And I'm Nanju. I'm a software engineer from Microsoft. I work in Azure HD Insight team. I work on Spark streaming, stress streaming service in Azure. And I also serve as committee member of XGBoost in DMLC and Apache MaxNet. I also contribute to Spark. So Arijit?
Hi, my name is Arijit Tarafdar, and I also work as a software engineer in Azure HD Insight. I worked with working with Spark for about a year in Spark streaming particularly. Previously, I worked with other distributed systems like Dryad Link and MPI. My research background is in graph coloring, and I contributed to a code called ADOLC, which is like automatic differentiation with operator overloading written in C++.
Okay. In today's talk, we will first introduce what is a continuous application and why we want to build such a new type of application. And specifically, we will talk about what are the challenges for us to build this application when we already have Spark in hand. And I will have a brief introduction about Azure EventHubs, which is a real-time message ingestion service on Azure. And we will review some concepts in stress streaming. And also, we will go into details about the key design considerations in building stress streaming connector. And later, Arijit will tell us how to test your connector implementation, and we will give a summary of the talk. So we know that nowadays, not only the size of the data, but also the velocity of the data is actually increasing. Different devices like sensors, like social networks are generating data continuously. And this data requires us to monitor them constantly and act up on them quickly. So to achieve this goal, the community proposed a new type of application called continuous application. It was mentioned since, I think, last Spark Summit. It was mentioned several times. In continuous application, we have real-time data sources. It generates continuous raw data. And then arrive to processing engine, we will have continuous insights from processing engine and produce to acting components. And acting components make the final action like block the fraud transactions, broadcast alerts. And thanks to Spark, we have Spark streaming, stress streaming for us to build a processing engine. We can get real-time insights in an easy way. The problem is we have so many types of real-time data sources. How can we connect Spark with these data sources? So in today's talk, the major topic is about how to build a connector for real-time data sources and stress streaming. We will use Azure EventHubs as an example, and we will compare it with the community's Kafka connector and show the key design consideration for us to develop such a stress streaming connector. So first, I will talk about what is Azure EventHubs. Azure EventHubs is a real-time message ingestion service. You can, in high level, it has the same functionality with Kafka. So like Kafka, it also has multiple partitions within each instance of EventHubs to scale the throughput. The best thing for EventHubs is that it is shipped to the customer as a service. So we don't have any concept like a cluster, like cluster. So users don't need to worry about how to monitor or operate on the Azure EventHubs cluster. All they need to care about is how to send data and receive data. Everything is handled in the cloud. So what is stress streaming? Stress streaming is a relatively new component in Spark. It was introduced in Spark 2 and keep evolving from 2.0 to 2.2. It is a streaming analytic engine for structured data. It shares the same set of APIs with Spark SQL, and the users can use these APIs to describe their computations, and stress streaming internal will apply these computations over the continuously arriving data and keep updating the results. In stress streaming, at least until 2.1, we still follow the micro-batch streaming model. That means the data comes from input to processing and to output in micro-batches. In input side, stress streaming provides a trait called source. This is for the developer of the connector to describe their real-time data sources. Specifically, when you want to connect stress streaming with your real-time data source, you have to implement two APIs. First is get offset. This API returns the last offset of the message in the undergoing batch. And the second API is get batch. This API just builds the data frame for the undergoing batch. And then in processing engine, it will call the get offset and get batch, which are two APIs implemented in source side, and then apply the user-defined operations to define the data transforming task. All of these steps in processing engine part is handled by stress streaming internal, so user don't need to worry about that. Then in output side, stress streaming also provides a trait called sync. If you want to, for example, you want to save your data in HDFS, you have to implement the sync with FS sync, and specifically, you need to implement add batch API. By calling this add batch, the data frame defined in processing stage will be evaluated, and the final data will be saved to the target system. And since the major topic today is about how to build a connector, we will focus more on input side. And we will talk about how to implement these two APIs for your connector. For the second API, get batch, it's just the stress streaming internal will pass in the start offset and the end offset, and then you can just build the data frame. So this is not a big deal. The key factor is in the first API, get offset. It needs to return the last offset of the next batch. So to get this value, we have to calculate two values. First is the end offset of the last batch. And then because, for example, we have a Spark cluster, it is with a certain capacity, we don't want to crash our cluster with too much data, then we need to do some rate control on our streaming pipeline. Then the next thing to calculate is about rate in the current batch. Then it will involve two questions: how to represent the offset and how to define the rate. For rate, to avoid tracking the size of every message, we usually define the rate as the number of messages. So how to represent the offset? For this question, we usually have multiple ways to do that. First, we can use consecutive numbers to address our messages. For example, we use 0, 1, 2, 3, and Kafka, MQTT, these systems will use this approach. By using consecutive numbers, we have to introduce some server-side index to map these 0, 1, 2, 3 to the actual offset of your message in your disk space. If we don't want to have this server-side index, we can use the size of the message to the real offset of the message to address that. For example, Azure EventHubs. The first message is addressed by 0, and the second message is addressed by the size of the first message. And then we don't need to have any server-side index, and the offset is passed as a part of the message to the user. So why the difference on offset representation will bring the difference to the connector implementation? So let's see the next example. Suppose we are using Kafka in our streaming pipeline. In first batch, okay, we start from 0, and we want to process 1,000 messages. And after we finish batch 0, we come to the next batch, and we start from 999 and process another 1,000. Okay, everything looks very straightforward. How about we use EventHubs? When we use EventHubs, in the first batch, it looks very similar. So we start from 0, and then we process 1,000 message. Then when we come to the next batch, we have to fill the value for the end offset of the last batch. Last batch is batch 0. The problem here is that Azure EventHubs does not use consecutive numbers to address the message. So we cannot simply fill 999 here. the driver side actually does not know what is the real offset of the message, the last offset of the last batch. So who knows this information? Only the executor, as the message is received by the executor and the offset is passed as the part of the message. Because of this, we have to build a channel to pass information from executors to drivers. Because of this channel, we have different implementation of get offset and get batch in Kafka connector and Azure EventHubs connector. In Kafka side, we can know the end offset of the last batch even before the batch is finished. So that's actually we just need to plus the rate with the 0 in our last example. But for Azure EventHubs, when we call get offset for the next batch, we have to first collect the ending offset of last batch from executors to drivers, and then calculate the target offset. For get batch, because we know the batch before, we know the offset before the batch is finished, Strut streaming internal will pass in the values, and we can use the passed in values as a start offset. But for Azure EventHubs, we need to use the collected result from the executors as the start offset. And there are more details about how we use a two-layered index to work with the offset log in Strut streaming. So that's too much for this discussion. We can talk more offline. Then the remaining question is how to build this channel bridging the executor and the driver. Let's see here, we have some source state frame, and we apply map over the source state frame. And then we get a transform data frame, and in each partition of this transform data frame, we will generate a file containing the last offset of the message in a certain EventHubs partition. Then what's the next step? We generate a file. Can we just let the driver side logic to read these files to get the end offset of last batch? Unfortunately, the answer is no. Let's consider APIs like head in data frame. For this kind of API, it will only evaluate some of the partitions in data frame. That means in different partitions, you will get a different number of files. And because of this, we have to merge the latest files with the historical results, and then commit, and then direct the driver-side logic to read the committed results. And since we mentioned the commit here, we have to ensure that all the streams offset are committed transactionally. For those partially committed or merged results, we have to have additional mechanism to discard those results and rerun the batch. So the takeaway here is that data source is not only designed for your Strut streaming connector. They have their own design considerations. For example, they want to have simpler server-side design. So as the developer of a Strut streaming connector, we have to accommodate our design with data source side design considerations. And then among all these factors in data source side, the message addressing mechanism is the most important one, as it will bring different requirements. For example, here we have to bring up a new channel between executors and drivers to share information. And then we have to introduce an additional mechanism to ensure the correctness of the channel. So next, I will give the stage to Arjit. He will talk about how to test the connector.
Thank you, Nan. So no development is complete without testing. So I will talk about how we did unit testing on this now that we have a connector. We also do integration testing, which we will not cover today. So when we looked at how we should do unit testing, we definitely looked in what Spark is providing, and Spark does provide a structure streaming unit testing framework. And these are our takeaways. So it's basically an action-based streaming testing framework where we can add compose test with actions like start streaming, add data, check answer, advanced clock, stop stream, etc. Then we looked into the Kafka tests, unit tests, and we figured that Kafka uses microservice. So they actually initialize equivalent of a Kafka cluster, you can say that. So given those, we found that the unit test framework is not actually usable as is in our context. And I will cover why they are not, it is not usable. So while looking at EventHubs source, the characteristics that jumped out are EventHubs doesn't have a Kafka type microservice. And when we do unit test, we really do not want to actually initialize a real EventHubs source, which actually talks to EventHubs in Azure. And EventHubs source actually underneath uses two clients. One is the EventHubs AMQP client, which actually does the data transfer. And there is another client we currently need to use is the REST client that actually gives us what is the largest offset in a partition, and we need that information from time to time. This REST client will go away, but currently we need to handle those. And for our unit testing, the goal is actually to replace these two clients in the source before we actually give to the first call of the EventHub source. So what are the issues with the unit test framework that Spark provides that we felt should be addressed? So there is no separation between test setup and test execution. Just because we are using simulated EventHubs, we really need that demarcation. Before we set up the test, then we can start the actual execution. The unreliable update of the EventHubs client is, of course, our own doing, and that is because in the Spark code, the streaming query manager.start query is asynchronous, and that brings us a REST condition for the way we are using it. And then we also face some task serialization issue with the add data, which is a trait that the framework provides. And we were supposed to implement that trait to add actually the data to the source. So what is the asynchrony problem or the REST condition? So the green is the Spark source code, and the purple is the EventHubs test code. So we use, the framework actually uses the start query method. So we give a start query method, and then the source is actually loaded. Only after the source is loaded, we can actually set the EventHubs client, which is the REST client, and the EventHubs receiver, which is the AMQP client. So what we found is, inside the start query, the Spark code calls create query. Only after the create query, of course, the source is available. Now, another call it makes is actually to start the execution. The reason that is in red, I will explain why. Now, this is in one thread. The APIs that get called within that black dotted boxes are in single thread. Start query actually starts, stream execution.start actually starts another thread. And the execution of thread 1 and thread 2, of course, is not in our control. So what we've sometimes hit is, before even we could actually change the EventHubs client and the EventHubs receiver to our simulated version, it actually makes a call to the source, and the source doesn't work because there is no real EventHubs backing it. Ideally, what we want to do is, we want to actually call create query, which is a private method, by the way, part of Spark code. Then we set the EventHub REST client, the EventHub AMQP client, and then give the call to start. So actually not using start query directly. And so all these things run in thread 1, and once we have already set the EventHubs clients to the simulated ones, we can actually let the test run. Well, as I said, that this is part of Spark code, so refactoring the real Spark code requires a Jira, and there is a process. So what we came up with is actually Nan's hack. We actually invoke the create query using reflection, set our current query to the active query. Then only we can get hold of the EventHubs source, and then we can replace the clients. After we got hold of the source through sources.head, we do our replacements, and then we do an explicit call to start. This way, we actually eliminated our REST condition. The second one is the task serialization issue. I'm sure that in many applications you have faced it, and you have refactored your code to actually avoided, and we faced a similar issue. Of course, it is our own doing because we have a simulated EventHubs. So the framework gives us stream test. This is part of the Spark framework. This gives a stream test trait. They give a add data trait, which we are supposed to implement. So we implemented add EventHubs data, which actually adds data to the simulated EventHubs. That is called as part of the simulated EventHubs. And since we are using simulated sources, the instances need to be shipped to the executors, which calls the EventHubs receiver, and which is called as part of each partition of the EventHubs RDD. So the problem is here, that we have to ship the instance of the simulated EventHubs to the executors. And why is it a problem? The problem is because stream test, if you look at it, calls query test. This is also part of Spark code, which calls plan test, which calls Spark fun suite, and which calls fun suite. The version of the fun suite that Spark 2.1 uses is not serializable, and that's where it breaks down for us. The solution is simple, of course. We just refactored the code, so the result of this, we could not use the stream test directly, so we divided stream test into two parts. One is EventHubs stream test, and the other part is EventHubs add data, which actually these are the two traits, and if you look at the EventHubs add data does not have any link to the fun suite, so serialization problem is gone. After all these changes, we can now compose test, and they are very similar to how Kafka sources are tested, unit tested. We can have sequence of actions like start stream, check answer, add EventHubs data, advanced manual clock, check answer, stop stream, etc. So after all this, we do have a experimental production get Spark streaming connectors. It's experimental in the sense that as soon as Spark 2.2 declares that structure streaming is production grade, we are production grade. We have designed, implemented, and tested structure streaming connector, accommodated the connector implementation, as Nan has described, with EventHubs source, which has some significant difference how Kafka is implemented. We do have the unit test framework that we believe will be helpful if somebody decides to write connectors for other sources, which are very similar to EventHubs. And we have actually resolved the rest condition. And we hope that the production code is also refactored in due course. Contributing back to the community while developing, we filed a couple of JIRAs. The most important, I would actually point out the first one. This is actually can affect if you're using Kafka and you're using APIs like reduce by window and you recover from a failure. You may end up with the wrong sequence of data. And with that, I will like to say thank you. We have open sourced our Spark EventHubs code. This is our GitHub location. And our actual offering for Spark is actually HD Insight on Azure. With that, thank you very much for listening.